Hello viewers, thank you very much for watching Gibbs TV. Today's video will be looking at when to use the appropriate regression technique. Let's get into it. Specifically, we'll be talking about the regression and the scale of measurement. Regression analysis describes the relationship between a set of independent variables and a dependent variable. There are numerous types of regression models that students or researchers can use. However, the choice often depends on the kinds of scale of measurement for the steady variables or the data set you have for the dependent variable and the type of model that provides the best fit. In this video, I will cover more common types of regression analysis and how to decide which one is the right for your data set or your study variable. Some properties of regression coefficient. Regression coefficient represent the slope of the respective lines of regression. So if you have your y-axis and the x-axis, the point of the intersection of the two regression lines always fall between the x and the y. Then a regression coefficient represents the increment in the value of the dependent variable corresponding to a unit change in the value of the independent variable. There are types of regression model. We have the simple regression and the multiple regression. And under each, we may have the linear and nonlinear regression models. So if you look at the model specification, maybe if you are doing your dissertation or your thesis, always under the section for model specification, you have to state your model. So always you have to state your y, and you state your x's. So you state your dependent variable and the independent variable. So for a simple regression model, always we have only one independent variable and one dependent variable. So in this particular equation or simple regression model, you see that we have our y, that is the dependent variable. We have our b0, that is the intercept or the constant term. Then we have the coefficient of the x. Okay, the coefficient of the independent variable is also known as the slope coefficient, the population slope coefficient. Okay, the slope of the x. It also serves as the unit change, okay, in the y that is caused by the x. Then we have the error term that is also here. Then we have the multiple regression. For the multiple regression model, you have more than one independent variable. So in this particular case, we have y, the dependent variable, that's the response variable, the criterion variable. Then we have two or more independent variables, which are the predictors or the regressors. You have x1, x2, s3, s4, up to the sk or the xn. We have our error term already here. So if you maybe your independent variable, you have about 5, it means you have 5 x's. You have about 6, you have 6 x's. All right. Okay, so take note of that. Then we have the slope of each independent variable. So b1 becomes the slope, b2 or the beta 2 becomes the slope. Okay, it doesn't matter whether you're using alpha, beta, or you are using A, B, C, D. So you have to define them. Okay, what A means, what B means. If you're using betas, you have to define what beta means. Okay, so if you're using alpha, you have to define what alpha means. So every variable that you use, you need to define them. You need to define your y. If maybe your y is about length of life, or your life is about education level, you have to define it. Very important to note that. Types of regression. Regression analysis with continuous dependent variables. They are measurement on the continuous scale, such as weight, time, and length. So based on regression analysis with continuous dependent variables, we have different types of regression models. We have the linear regression, we have the advanced linear regression, which we have the ridge regression, we have the lasso regression, we have the partial least square regression, and some other nonlinear regression as well. With regression analysis with categorical dependent variable, Here, a categorical variable has values that you can put into a countable number of distinct groups based on characteristics such as sex, age, group, marital status, educational level, and several other categories. So under this particular session, we have different regression types. That we have the logistic regression, where under the logistic, we have different forms of advanced form of logistics. We have the binary logistics, we have the ordinal logistics, we have the nominal or the multinomial logistics regression. Then we also have regression analysis with count-dependent variables. And counts are non-negative integers from 0, 1, 2, 3 up to infinity. So regression types under this category, we have the Poisson's regression, and we also have alternative to the Poisson regression because there are some data that may violate the Poisson, but it follows non-negative integers. So some of them include the negative binomial regression, and we have the zero inflated models. So let's get into them. Regression analysis with continuous dependent variables. Here we have the linear regression under the continuous dependent variables. So linear regression, also known as the ordinal least squares, that is the OLS. Linear least squares is the real workhorse or the pillar of the regression world. Okay, the benchmark, the foundation for most of the regression world. We use linear regression to understand the mean change in the dependent variable given a one unit change in each independent variable. Note also that researchers can also use polynomials, okay, to model curvature and include interaction effects despite the term linear models, and this type can be model curvature. So in this case, a linear model that uses a polynomial to model curvature. It's a linear, but it's curved. OLS produces the fitted line that minimizes the sum of square differences between the data points, okay, on the line. The next, another continuous dependent variable is the rich regression. Rich regression allows you to analyze data even when severe multicollinearity is present and helps prevent overfitting. So if you check the data and you realize that there is a presence of multicollinearity and you want to still overcome it, all right, then you can use the ridge regression, because ridge regression allows you to analyze data even when severe multicollinearity is present and help prevent overfitting or spirals results. This type of model reduces the large problematic variance that multicollinearity causes by introducing a slight bias in the estimates. So in this case, you see that the procedure traces away variance in exchange of a little bias, which produces more useful coefficients, okay? So the ridge regression coefficient estimates some value which is always greater than 0, which produces more useful coefficients estimate when multicollinearity is present. So it's a good technique or models when you observe that your data, there is some presence of multicollinearity, and it's a good idea to use ridge regression. Next is the lasso regression. Lasso regression, which is the least absolute shrinkage and selection operator, performs variable selection that aims to increase prediction accuracy by identifying a simpler model. It is similar to the ridge regression, but with variable selection. So in this particular, it's similar to the ridge regression, but it is always deals with variable selection. The next is the partial least squares regression. Partial least square regression is useful when you have very few observations compared to the number of independent variables. So if you have few n, okay, when you have few n, that is a sample or observation that is compared to the number of the independent variables, the x's. Or when your independent variables are highly correlated, when they are also highly correlated, there is some element of collinearity. Then you can also utilize the partial least square as well. Partial least squares regression decreases the independent variables down to a smaller number of uncorrelated components using principal component analysis. Okay. If you look at it, you have the principal component analysis. Then the procedure performs linear regression on these components rather than the original data. So the partial least squares emphasizes developing predictive models and is not used for screening variables. No. Unlike OLS, you can include multiple continuous dependent variables. So the PLS uses the correlation structure to identify smaller effects and model multivariate patterns in the dependent variables. If you look at this, this is a partial least square regression model comparing the two axes. You have regression analysis with categorical dependent variables, categories, nominal variables as well. And one of them is the logistic regression, which is part of some of the regression models that align with categorical variable. So logistic regression transforms the dependent variable and then uses maximum likelihood estimation rather than the least squares to estimate the parameters. Logistic regression describes the relationship between a set of independent variables and a categorical dependent variable. So as long as the dependent variable is categorical, you cannot use OLS or you cannot use those linear regression models. However, then you can utilize logistic regression if it has a categorical dependent variable. But there are different forms or advanced types of logistic regression. So choose the type of logistic regression model based on the type of categorical dependent variable that you have. So the scale of measurement is very key here. If it's just binary, then you need to know the type of logistics to use. If it's ordered, you need to know the type of logistic regression to use. And if it is in terms of more than 3 categories, 4 categories going to, you need to also identify the best logistic regression to use. So the first one is the binary logistic regression. Talk about it here. Use binary logistic regression to understand how changes in the independent variables are associated with changes in the probability of an event occurring. This type of model requires a binary dependent variable, two case category. A binary variable has only 2 possible values, such as pass and fail, employ or unemploy, win or lose. They are all in 2 folds, 2 possible values. Example, political scientists assess the odds of the incumbent US president winning re-election based on stock market performance. So it assesses the odds of whether it will win based on re-election or lose. Very important. So it's 2 possible values outcome. The next is ordinal logistic regression. Ordinal logistic regression models the relationship between a set of predictors and an ordinal response variables. An ordinal response has at least 3 groups. Take note of that, at least 3 groups, which have a natural order such as hot, medium, and cold. Example, market analysts want to determine which variables influence the decision to buy large, medium, or small popcorn at the movie theater. The next is the nominal logistic regression. The nominal logistic regression, also known as the multinomial logistic regression in some textbooks, models the relationship between a set of independent variable and a nominal dependent variable. A nominal variable has at least 3 groups, which do not have a natural order, such as scratch, dent, and tear. So in this case, it's not ordered, all right, but it has more categories. Example, a quality analyst studies the variables that affect the odds of the types of product defect, whether the product has some scratches, dents, and tears. That is a good idea to utilize nominal logistics or multinomial logistic regression. Still on the nominal and the multinomial logistic regression. In statistics, multinomial logistic regression is a classification model that generalizes logistic regression to multiple class problems with more than 2 possible discrete outcomes. That is, it is a model that is used to predict the probability of the different possible outcomes of a categorically distributed dependent variable, given a set of independent variables which may be real valued, binary valid, or categorical valid, and many others. Multinomial logistic regression is known by a variety of other names outside that of the nominal logistic regression. It's also known as polytomous logistic regression, multi-class logistic regression. We have the softmax regression, have the multinomial logit or M-logit, or the maximum entropy, that is a max-ent classifier, and we also have the conditional maximum entropy model. All these names can also be used to describe multinomial logistic regression in different textbooks. Example, multinomial logistic regression is used when the dependent variable in the question is nominal, which is equivalent to category, and for which there are more than 2 categories, not just 2. If it's only 2, then you need to go and use the binary. All right, or the binomial. Some examples include 1, which measure will a college student choose, given their grades, stated likes and dislikes? Which blood types does a person have, given the results of various diagnostic tests? In hands-free mobile phone dialing application, which person's name was spoken, given various properties of the speech signal? Also, which candidate will a person vote for? Or we have more candidates, given a particular demographic characteristics we want to test. Then which country would a firm locate an office? Okay, given the characteristics of the firm and of the various candidate countries. So all these things, you see that we have the dependent variable, we have more than 2 categories. The next is regression analysis with count-dependent variables. If your dependent variable is a count of items, events, results, or activities, you might need to use a different types of regression model. Counts are non-negative integers, which start from 0, 1, 2, 3, 4, up to infinity. Count data with higher means tends to be normally distributed, and you can often use OLS. So if you are dealing with count numbers, that is numerical data that has a higher means, maybe talking of 2010, 12 going, okay, they are all in higher means, then it's an appropriate 30-100. It's an appropriate to use ordinary least square linear model. But if the means tends to fall within a single digit, 8, 9, 10, 4, then it's a good idea to use what do you call it, non-negative integers models. So let's look at some of them. Count data with smaller means can be skewed, and linear regression might have a hard time fitting this data. So for these cases, there are several types of models that you can use when you are dealing with data sets that the mean has smaller means and skew data. The first is the Poisson's regression. Count data frequently follows the Poisson distribution, which makes Poisson regression a good possibility. Poisson variables are counts of something over a constant amount of time, area, or another consistent length of observation. All right, so use Poisson regression to model how changes in the dependent variables are associated with the changes in the counts. With a Poisson variable, you can calculate and assess the rate of occurrence. A class example of a Poisson dataset is provided by the the Butkiewicz, a Russian economist who analyzed annual deaths caused by hostages in the Prussian army from 1875 to 1894. Poisson's models are similar to logistic models because they use the maximum likelihood estimation and also transform the dependent variable using the natural log. Poisson models can be suitable for rate data. When you're dealing with rate data, then you can utilize Poisson's models, crime rate, all those things. So Poisson models can be suitable for rate data, where the rate is a count of events divided by the measure of that unit exposure, a consistent unit of observation. Then you can use Poisson's model. For example, homicides per month, homicides rate, homicides per month. Another specific example is an analyst uses Poisson's regression to model the number of calls that a call center receives daily. Here too, you can use the Poisson's regression model. Alternatively, the Poisson's regression for count data. Not all count data follow the Poisson distribution because this distribution has some stringent restrictions. Fortunately, there are alternative analyses you can perform when you have such count data. The first is the negative binomial regression. Poisson regressions assume that the variance equal the mean. It's always assumed that the variance equals the mean because it has a constant intervals. When the variance is greater than the mean, then your model has over dispersion. If the variance is always greater than the mean, then the model has over dispersion. Then you can't use Poisson's regression because Poisson's assumes equal variance to that of the mean. So when the variance is more than or greater than that of the mean, then you cannot use the Poisson's regression. In this case, a negative binomial model could be a best fit because a negative binomial model, also known as the MB2, can be more appropriate when over-dispersion is present. In the probability theory and statistics, the negative binomial distribution is a discrete probability distribution that models the number of failures in a sequence of independent and identically distributed Bernoulli trials before a specified non-random numbers of successes occurs. So always with the the Bernoulli utility function or Bernoulli trials, you may have two possible outcomes, okay? Whether the thing occurred or it did not occur. And that is how the negative binomial model follows. For example, we can define rolling a 6 on a dice as a success and rolling any other number as a failure. So it's either success or failure. It's two possible outcomes, which is tied to probability outcomes. So if you don't get 6 die outcome, then it means any other outcome that comes is a failure. And that's how many failures rolls will occur before we see the third success. In such a case, the probability distribution of the number of failures that appears will be a negative binomial distribution. Example, hospital length of stay is an example of real-world data that can be modeled well with a negative binomial distribution through negative binomial regression. Very important to know that, you know. The last concept that I'm talking about is the zero inflated models. Sometimes your count data might have too many zeros to follow the Poisson's or even the negative binomial regression model. In other words, there are many or more zeros than Poisson's regression predicts. In this case, zero inflated models will be very much appropriate for such data sets. This is because zero inflated models assume that two separate processes work together to produce excessive zeros. That is, one process determines whether there are zero events or more than zero events, while the other is the Poisson's process that determines how many events occur, some of which can be zero. Example, suppose park rangers count the number of fish caught by each park visitors as they exit the park. In this case, a zero inflated model might be appropriate for this scenario because there are two processes for catching zero fish. One, some park visitors catch zero fish because they did not go fishing. Then the last scenario is that other visitors went fishing and some of these people caught zero fish. The fact that you went for fish does not mean you will catch. Thank you very much for subscribing to Gibbs TV, and I will see you all in the next video.